Gaussian shift model, we have looked at the Bernoulli model, now we look at the Poisson model. Any idea why we are looking at this sequence of models? The sum of the observations, again, turning up in the maximum likelihood estimate. So everybody, I think, knows the Poisson model. I give two applications here, two different PDFs for different lambdas. Here you see the corresponding CDF. Typical applications are telephone calls arriving at a switchboard, or more modern application is web requests arriving in a server. So you have to scale the network according to estimated maximum likelihood estimated parameters in a Poisson model when you try to make a network based on web pages. So let's look at more details here. And the alpha-based confidence interval, again, we discover the log likelihood ratio has a simple form, and it is connected to the Kullback-Leibler by n times Kullback-Leibler is the expected value of the likelihood ratio. And here written in two terms, difference of the log likelihood. And you see that the S comes in again, and the form of the Kullback-Leibler is given down here, with which you can construct an alpha confidence set. I'm sorry, I forgot to switch this on. Thank you. Thank you. On which you can construct an alpha confidence set in the following way. As Ruslan said, we are looking at essentially at exponential families. So we have now looked at Gaussian shift models, Poisson model, Bernoulli model, and we are still in this set here. Later tonight we will see how this will be extended to more general so-called regression-like models, where we use local parametric families. But for exponential families, the likelihood in general, in an exponential model also belongs to this exponential family. In this case, the PDF or the distribution function is given by e to the minus t over tau. The likelihood is again a very simple form, involves the sum of the y observations, and we again rediscover the relation between the Kullback-Leibler and the likelihood ratio. Very short summary here. Kullback-Leibler for Poisson law and for exponential law has very similar form. It's given on this summary slide. And one of the applications that we'll give tomorrow afternoon before we enter the other talks is the volatility, so-called volatility model. In this case, the unknown parameter is the scaling parameter theta, for the moment here, normal distribution. In fact, the theorems that you will see will all involve either exponential families or things that are connected with the normal distribution. If you want to have something like a so-called GH distribution, it lies a little bit outside, so you have to do a little bit more additional work to cover also that gap, GH, generalized hyperbolic distribution. But these are things that we have done in several papers. Here we will present the family or the results based on normal psi. So we observe, say, this squared psi's. That means expected value of the squared psi's, you can see immediately is equal to theta. You can calculate the likelihood, and again the likelihood involves the sum of the y's, but each y is now square observation, squared psi's. The theory that is presented covers this likelihood, covers this volatility model as well. And the Kullback-Leibler divergence is given down here for the volatility model. Okay, now more general, as Ruslan said, we can put all this stuff into a so-called exponential family, where the PDF is given in the following form: p y theta, then a function p and y, and parameters c and beta in the c and b in the exponent. There is a relation between b and c if we parameterize this exponential family in the so-called natural way. This means that the expected value under theta of y, having this density here, is equal to theta. Then the natural parameterization gives you, or entails that b prime, the first derivative of this function b with respect to theta, must be equal to theta times c prime. Again, you can calculate the Kullback-Leibler divergence. So everything that I showed you before falls under these exponential families. I show you two more transparencies, and then Voltaire will take over. I was talking about Gaussian Bernoulli-Poisson exponential volatility model, and I showed you on different transparencies all these Kullback-Leibler divergences. And here I give you the Fisher information, which is given also in your notation handout on page 04. Page 04, there's a theta missing on page 04. I theta. In an exponential family, you rediscover this dependence on S, on the sum of the yi's, and you rediscover again the relation between a log likelihood ratio and the Kullback-Leibler distance in a parametric model, divergence in a parametric model, when you evaluate it at theta below and theta. So, very simple summary. It's not really, this first part is not really a necessary summary. This down here is the important thing. When we have an exponential family, we have seen 5 or 6 of these distributions. They can all be, the Kullback-Leibler divergence for an exponential family can all be rewritten in terms of these functions c and b, and the formula is given down here. Now, Voltaire will give the first theorem on the fitted likelihood. Yes? You did this?
Right now.
And then we have a break after this transparencies. This is down.
Okay, so maybe I go a little bit back, and I will try to summarize the discoveries which we have for different models considered here in this table. So actually we can observe some common features for all such models, and historically it was exactly like this. I went through all these examples and realized that each example looks very similarly to the previous one, and then it was a question why it is always the same in the same form. And here is again the question what the mathematic is. The mathematic is a science for generalization. If you observe many times the same, you can generalize and derive some law. So in this sense, this was the question: what is common here? And maybe I try to summarize. So what was common for all these models, and what we can generalize? And actually, what we have for every model, we have a likelihood expression L of theta, and our estimate is theta tilde is the maximum of L of theta, And what we are interested in, not only the point of maximum, theta tilde is a point of maximum, okay? But actually, what is interesting is the value of maximum. This is a maximum of L of theta. This is a very important object, and we will see this object plays a very important role in the whole theory. And actually, we consider not this one, but the deviation, L theta tilde theta, is the maximum over theta. Well, here particular value is theta prime. It's maximum again over theta, L of theta minus L of theta prime. So we fix some point and look what is the deviation of the likelihood with fixed value of theta prime, and here we take the maximum over all possible values. And what we realized here, for all these families, our discoveries can be summarized as follows. First discovery is that theta tilde is for all families as a mean value is 1 over n, the sum of yi. This is the first discovery. Can you see this? No.
Oh yes. That's why we have developed the transparencies volunteer.
Okay, but
to avoid these unseeable things.
But I would like to keep it on the blackboard. I don't know whether we have it here. Yeah, here.
It's here. It's all here.
And the second discovery, it is written here, that this value of likelihood is n times the Kullback-Leibler divergence between theta tilde and theta. So this is the two discoveries which are common for all the families. And then the question is why it is like this. So, and it turns out all these examples belong to this exponential family with a canonical parameterization. And this canonical parameterization, I go back.
Natural parameterization.
Natural parameterization.
Yes.
Sorry. I have to learn this. So this natural parameterization means this very simple property that expected value of y under theta is equal to theta. And if you look at this property, you can immediately understand why the maximum likelihood is the mean value. Because for one particular observation, the mean is exactly theta. Therefore, if you have n independent observation, it's very natural to take the mean value, and again you will have this property. Okay? So now actually we have another property here. This b prime is theta times c prime from this equation, and this property is also very useful. And with this property you can derive very easily this identity. So you can derive, first of all, that theta tilde, which is obtained by maximizing this expression. So you can derive this to an identity from this simple property. So I don't know this volatility model. One moment, why it doesn't go? It is here. Here. This is exponential model. Well, do I go in the right direction? Probably I go in the wrong direction. This is the reason. Here. Okay. So now I'm right for exponential family. So you have this expression for the, so this is the density, probability density for exponential family. Then you can derive this log likelihood. It is the, this compact expression with two sums, S and R. And if you differentiate this equation with respect to theta, and use this identity, so you differentiate, you use this identity, then C prime theta will cancel, and you arrive at this identity. Okay? So this is the idea, and if you plug in this theta tilde in the likelihood, you get this identity. And this quantity, this deviation of the maximum likelihood over one particular value, it is called fitted likelihood. And this fitted likelihood will be systematically used in our course. Okay?
It should be there. It should be said that this is called fitted likelihood.
It was not said, so...
I didn't say it there. I should have said it.
Yeah, this is called fitted likelihood because we fit the likelihood to the data. And this fitted likelihood is n times Kullback divergence between the theta tilde, the estimate in one particular value. Okay? So now all this stuff was very classical till now. It's a summary. And now we make a huge jump. So this classical theory is at least 50 years old. At least, maybe 60. What was explained before about exponential family, etc. And now I present one result, which was published, you see here, 2005. Okay? And so I was really surprised about this result, so you can discover something in the model which is absolutely classical. But still, this is a result which we cannot failed to find in the literature, and the result claims the following. Assume the theta star is a true model, as usual, and we look at the deviation of the likelihood over the value at the true point. So I recall theta tilde, theta star is the difference between the fitted likelihood optimized to the data and this likelihood at the true value. And the result says that this guy should not be too large, cannot be too large in probability. It exceeds the prescribed value z at most with the probability 2 times e to the minus z. This means this probability is exponentially small, and this is what is surprising. This is exact and independent of the sample size. So here in this L, I recall, in this L, you have n hidden. So look here, this fitted likelihood n times something. But in the right-hand side, you don't have n. Here you don't have n. And if you put it exactly here, or you can derive from this result also the corollary about the risk. So this what mentioned many times. This is a theorem number 1. That the risk measured by this likelihood. If we take the likelihood to the power r. This is exactly n to the r, expected value of the Kullback to the r, and this guy is bounded. So you see here you have a huge multiplier, n to the power r. Yeah, but here you have the fixed value. And why it is possible? This means that this Kullback between theta tilde and theta star is very small. This is the meaning of this result. That this Kullback between theta tilde and theta star is actually of the rate 1 over n. And this means that theta tilde is very close to theta star. Okay? And what is the meaning of this result? So theta star is a maximizer of the expected value of the likelihood. By definition. Because here you have 0. So theta star maximize expected value, theta tilde maximize the empirical counterpart. Likelihood is the empirical counterpart of the mean value. And the result says that basically theta tilde is very close to the true value, in the sense that the deviation measured in the term of the likelihood is stochastically bounded. So this is the result.
Why is it surprising?
Why it is surprising?
Is it surprising?
No,
It's natural, right?
no, it's nice actually. I don't say it's surprising, but so surprising is probably that it can be written in this such a general and compact form. So you see here, this bound is independent of the sample size. It's independent of the parametric family, except we assume that this is an exponential family. For any exponential family, we have this inequality. And therefore, we have this risk bound. So this is a rather general result without any further assumption. It's exact and non-asymptotic. And the result has some further corollaries. But first, before I go to this corollary, the other question is, okay, this result is so nice, but it is established for exponential families. So for instance, if you consider the volatility model, this means the volatility parameter is unknown, so the variance, but it assumes the normal innovations. And now this is a question which Morgan asked me many times: what happens with this result if the innovations are not normal at all?
It took me 5 years until you went there.
Okay, so it
took
took
5 years.
it took some time to me to answer this question. What happens if we deviate from exponential family? So we will see this result is extremely useful. You can build the whole theory only on this particular result. But this theory is restricted to exponential families. Could we go out? Could we extend this? And this is a question which we are still trying to answer. And there is another result which is so recent that actually is not yet published. There is even no preprint about this. There is only a draft version of this result.
So there's already a text file.
No, so I have it with me, the paper, but it's not finished, not even in the form of preprint. But the result is proved carefully, so I mean no doubts on this, but not yet published in any form. And the result says, if you have arbitrary parametric family, more or less arbitrary, under some regularity conditions on this family, you can establish the same type of bounds which you have for exponential family. I recall what we have for exponential family. See here, you have expected value of the fitted likelihood is bounded by a constant. To the power r is bounded by a constant depending on r only. Okay, I'm almost ready. And now, what we have here, the same kind of results, but here we have arbitrary parametric family, and this constant here is kind of absolute constant. It depends on the parametric family, but not on the sample size. Actually, it depends only on the entropy of this family. And for exponential families, the entropy is very small. Generally, it's larger, but still it is some constant here. And we are not very much interested in this constant because this is a kind of existence theory. We don't need to write it, use it explicitly. But important is the left-hand side depends on n, and the right-hand side is fixed. And what are the corollaries of this general bound? Particularly, in the regular situation, you can make a kind of quadratic expansion of the likelihood. So you can derive the quadratic expansion of L theta tilde theta star with respect to theta tilde, and the linear term will cancel because theta tilde is a point of maximum. Around the point of maximum, you have always quadratic representation of the function. So around the point of maximum, it is quadratic, and therefore you have this expression. And actually, in the regular situation, here the term between is more or less n times the Fisher information matrix. And therefore, if you plug this quadratic expansion in the previous bound, you can get the following inequality. I only show the first one. And this inequality basically says that theta tilde minus theta star multiplied by square root of the Fisher information matrix and multiplied by square root of n is bounded by a constant. And this means nothing but the root n consistency and kind of root n boundedness of the theta tilde. So this is a trivial and a free corollary of the previous result. This fact, which is very general, and actually this fact is more or less asymptotic because of this approximation, but the result before it was non-asymptotic, and therefore we will use this result directly later on. Okay. Another corollary, and this is the last what I would like to present today, is the corollary about the confidence sets. So basically what we know about this fitted likelihood.
Is there not a 2 missing? Or 2?
No. So what we know about this fitted likelihood? This guy, if theta star is a true value, this guy should be bounded. And therefore we can define the set of points for which this guy is bounded. So theta tilde is now fixed, and we consider all theta such as this inequality holds true with fixed bound z. And the previous result implies that the true value theta star belongs to the set with high probability, because we know that if we would have here stars, that this guy should be bounded. This is the idea. The previous result about boundedness of this fitted likelihood implies this structure of the confidence sets. The boundedness of this likelihood under the true measure. So once again, I show this. So we know this guy should be bounded, and therefore we build the confidence interval or confidence set on the base of the fitted likelihood. So we consider this set of points with respect to theta, and we know more or less with big probability that the true value should be here in this set. This is a corollary of the general bound. And this fact will be intensively used in the construction of our deductive procedures. That this is a true confidence set for the unknown parameter value theta if the parametric assumption is true. This is what was called theorem 1. First theorem in the whole theory, or type 1 theorem, that if the parametric assumption holds true, we can build everything on the likelihood. In particular, we can build the confidence sets which cover with big probability the unknown but true value theta star. Okay, I think this is the first part of the course about the theorem, about the first type theorem, about the parametric part.
The R's moment of Goodbach-Leibler distance of the log likelihood function was bounded with constants that are under control. Why is this important? Because from these distances we can calculate confidence sets. Now, we apply this to a so-called regression model. So this is one of the transparencies that does not follow the famous keep it at 7 rule. 7 lines and 7 words per line. But since you know it all, I thought we are here a little bit deviating from the rules that are given. So we just to introduce notation. F is the regression function, Y are the response observation, epsilon the errors. Recall that if epsilon is normal, then we get to the least squares problem, and if epsilon is, for example, exponential, we get to this least absolute deviation model. N is the sample size, x1 to xn is called the design, and the parametric case means that parametric case means that we are parametrizing the regression function in terms of a parametric model. One example, a very classical example, is of course the linear regression model. Homoscedastic error means that all the epsilons have the same variance. Heteroscedastic error means that the variance varies with the observations. Sorry, it's this one. So, yeah, I'm trying it. Yeah, now it works. Okay. So one applied example from the SPM book is the so-called wage equation. We've written this up in an economics flavor because we'll give this course, as I said, at RWI. Wage equation means that you try to infer your wage, or in this case it's the log wage, as a function of your investment into schooling or labor market experience. And there's a famous model by Bernd, very well-known applied econometrics book, where using the CPS, I think it's Consumer Population Survey, or I think PS stands for Population Survey, maybe C not for Consumer, from 1985 with 534 observations. He has modeled the regression function, this function f, as you can see, as a parametric model with a square term here in terms of schooling and experience. In the marginal dependence on schooling is linear, on experience it's nonlinear, which is because of the Procrustean bed of parametric modeling, a strange result, because it says actually that your wage will decrease, or log wage will decrease, when your experience increases. In the parametrically estimated regression surface, you will have this parabolic structure in terms of schooling and experience. And in schooling it's linear, and in terms of experience, which goes up here, it is parabolic, Procrustean bed, as I told you. Now, if you go for this approach that we have described here, the so-called non-parametric approach, you let the dependency on schooling and experience to be very flexible in terms of a so-called non-parametric regression function. This should be an F here, not an M, of course. Then you will get a function that looks like that, which makes much more sense, especially for high years of schooling, high years of experience. You actually have more wage when your experience increases. Another example where smoothing could help is the example of the calculation of the implied volatility surface. This is so well known, so that in this room, at least since 2002, that Roger told me I should make this very short. Just show you one implied volatility surface, a corresponding movie you can download from the internet. What is the difference between these smooth non-parametric surfaces that you have seen and the parametric model, for example, of Bernd for these wages as a function of schooling? We'll develop this in a general likelihood-based framework. Again, here I show you these minimum contrast estimators. A parametric model for this regression functions is the solution to a parametric optimization problem is given by the minimum of a contrast function in terms of the normal distribution. If the epsilon were normal, then you would receive here the least squares estimate, and the exponential you would have the least absolute estimate, and you receive back the likelihood estimate if you know or assume the likelihood, the PDF of epsilon, then you can write down the contrast as minus log pu. Here's a very famous example of the regression based on international phone calls from Belgium from 53 to 73. This example you find in the book of Museo, where he showed that the increase of telephone calls when you measure it by a least squares estimate. I think these are just wrong. The least squares estimate follows the outliers, and the LAD, which is the least absolute deviation estimate, which should be the red curve, lies closer to the original observation, is not influenced by these outlying, actually miscoded observations. Now, what we are entering now is the extension of the exponential family to so-called regression-like models, where the parameters of the exponential family, this was the theta, the parameters of the exponential family are actually regression functions that depend on other variables, which we call, of course, usually in regression problems, x. That's why it's called a regression-like model. So the setup that we are entering is that we have a parametric family, again dominated by another probability measure p. We have this density, parametric density, and we are thinking of a standard exponential family, could be normal, could be Poisson, etc. But the difference to what we have done here of this type 1 theorem now, where we were thinking of a parametric family that had just a parameter, now we let the parameter actually depend on design variables xi. You will see the relationship to kernel smoothing and to classical non-parametric smoothing in a second. So now that this difference between what we have done before is yi was just distributed with p, and then there was theta. Now this theta is a function of x I. Also this doesn't work. Okay. And natural parameterization, I should mention this once more. Natural parameterization is as the expected value under the parametric value. Of course, now the parametric value is dependent on xi. The expected value of y is equal to y. This is so-called the natural parameterization. Canonical is a different one. We don't use this one. We use the natural parameterization. Okay? So the natural parameterization, as I said once more, in the exponential family, before we had expected value of y under theta was equal to theta. That was the natural parameterization. Now, the expected value of y, but this is the true model, so I could probably write here. So we are in this space here, right? In this space out here. The true model, non-parametric model, no parametric anymore, is now f of xi. And of course, f of xi is an unknown function. F is an unknown function. If f is just equal to theta, then it would be back to the parametric model. It's just a constant function, then it's back in this square. That's what is written here. So f is equal to f theta, then we are back in this square. Parametric modeling, that means we are modeling the f function in terms of a parametric family, means we apply the maximum likelihood theory. Theta wiggle is the maximum of the likelihood function, as you see here. likelihood function yi and f theta, and we apply the maximum likelihood theory to get theta. So this is the example that I mentioned. Constant regression for an exponential family is what we have seen before. So take an exponential family, natural parameterization, and just say f theta is equal to theta. Then everything that we have seen before, like dinner, is the same thing as you have seen here. Theta beta is just the sum of the yi's. Now, in the case of this more complex dependence of the parameters, so this theta here is now a function of xi, we have to do a different approach. And I will motivate this by Corbin's method. Let us look at linear regression for the moment. So take basis functions, given basis function of fixed order, psi 1 to psi p. Parametric family is f theta is equal to the sum, weighted sum of this basis function, unknown parameter theta. So the likelihood function is given by the sum of the oak likelihoods at each observation. We assume, of course, an IID setting. Theta beta is the maximum, and we know very well the answer. We apply this in many cases, and this slide is only there to remind you that we are not doing anything completely different what you have done before. I give you an example where this classical economic exponential family stuff has been used. Is an old paper that I've written with Michael Burda, Marlene Müller, and Axel Werwatz. Appeared in the Journal of Applied Econometrics, I think. It's about East-West migration. In the beginning of the 90s, you know, unification was there. People went from the Eastern Germany to West Germany, and we wanted to model their likeliness to move to the West. So the variable that was recorded in the SOEP dataset, socio-economic panel, was that y is equal to 1 if a person moves to the West or imagines to move to the West, and 0 otherwise. So this statistical situation can be modeled by a binary choice model, as it is called in the econometric literature, or dose response models, as it is called in the biometric literature. And many people use either probit or logit models. Here I write to you for a logit model, which involves a function g, which is called the link function, or the inverse of the link function, a monotone function g, that is applied to a linear combination of x. So the basic idea is one asks the people in the SERP for certain variables, like their wage, like whether they have families in the West, whether they have relatives in the West, and other possible likely variables that could influence their decision to move to the West, and one tries to model this probability, the likeliness to move from East to West. Here is the logit model, and xi, as I say, are characteristic of these persons. But if you apply not a linear, this is called an index, it's a single index model, it's called an index in this kind of literature. If you apply a so-called single index model but with more flexible indices, actually a non-parametric fit, you observe in the logic model this red curve, which just says, for example, in this marginal effective income, it just says if income increases, then people will move to the West. The likeliness, the probability to move to the West increases. But if you fit this non-parametrically, you can actually then develop the test, paper in JASA with Alan Mammon, to test green versus red. If you plot a non-parametric curve and you fit a non-parametric curve, that means you go to this outer setup here, more flexible probability distributions, you will see that you get something much more reasonable. What does that curve, for example, mean as a function of income? It means that, for economists at least it makes a lot of sense, it means that you have people below a certain income level, sort of people that don't even have medium income, you can call them desperados, they are very keen on moving to the West. And you have also, then you have people in the center that are sort of probably waiting whether the situation in the East improves. And then you have highly trained people of a monthly income of 3,000 to 4,000 marks at that time, at the beginning of 1990, that can make even more money in the West than they have received, or they receive in the East. And that's why, again, they have a likeliness to move to the West. So the non-parametric setting gives you a much more reasonable model for this situation of migration from East to West. The rocket model correspondingly is just a monotone function as a function of this index. So you have to think of this non-parametric function. The parameter is here beta transpose x. In our case, it is not beta transpose x, it is an unknown function. In this case, it's actually an additive model or a semi-parametric additive model, partially linear model that we applied. But you have to think of different clustering of these variables that apply to the probability of moving to the machine.
Yeah. I don't know if I missed something, but is this example considered in this case when the parameter is depending on x or not?
Yes, this is the whole point. The parameter in the exponential family depends on x. See, the difference is the parametric model here. It's good that you've asked this question because I also had many difficulties. The parametric model, the thing that we make non-parametric here is not the full function. We don't make this function non-parametric. Only the index is done non-parametric. So the function beta transpose x is replaced by a function f of x. In this example that I have shown you in this paper with Axel Werwatz and Michael Borda and Marlene Müller, it is more complicated example that I don't want to give here. But important is, thanks for this question, important is that you replace the linear combination by some non-parametric relationship. Okay, so I said this already, a global parametric assumption, that means for all x the same parameter, is a Procrustean bed. For time series, for example, we would never believe that a time series model is the same, say, call it S&P 500 Gauge 1-1 for 25 or 50 years. We would certainly believe, and we can see this when we fit a parametric model in certain periods and blocks, we can see the parameter changes. So definitely a global fixed assumption, don't have to call it parametric, a global fixed assumption is this famous Procrustean bed, especially if the family is too simple, as we have seen here in this model of migration. But it is maybe also a Procrustean bed if it is too complex. And the approach that is followed here, like in smoothing, is to use the parametric assumption. That means this modelization only locally. That means, let me come back to the blackboard here one more time. So this was the situation that we are looking at, data, one model. Yeah? Now what we are doing is, because we are looking at regression models, here you have x, here you have y, if everything is fine, then you can use this central model for all x's. But suppose you have deviations here and there, then if you blow this up, if you blow this region up, right, locally, it looks again like a linear model. Because there's a famous theorem called Taylor expansion. Yeah? So locally, these models are again smooth or can be modeled hopefully with parametric models. So what you have to think of now, what you have seen was models of this kind, very fixed, and theorem 1 type. Now you have to think of this square being applied at different x points. Yeah? Then the first question is, what I lose, given here, this is exactly this bias, small modeling bias. What do I lose if I still, also I have the true function like this, if I still use this linear model? Yeah? Let me give you a simple example verbally. Do you remember the speed of convergence of the Gaussian shift model? Yi equals theta star plus epsilon I. What was the speed of convergence of theta wiggle? Was n to the minus 1/2. So that makes it clear if you vary theta star, suppose you don't have at each, I repeat this observation, but I don't take theta star, but I take theta star plus a sequence that tends to 0, but faster than n to the minus 1/2. You will not be able to see it statistically because it's under the scope of the variation, which is n to the minus 1/2, your variance. You will not see this small modeling bias, you will not see the bias, you will not see the variation of the true parameter. You will not be able to identify it if it converges. Yeah? So, the question that leads us to theorem types 2 is, how much do I lose? Yeah? When I have little wiggles, how much do I lose? In precision, in confidence intervals, in risk, in speed of convergence. The third type theorem is, I can say that, third type theorem, this is also an EP theorem, it's under P, under the true, so it's everything under the red, this outer red curve. And another distance, but here I have so-called adaptive estimate. You have a so-called oracle estimate, you have an adaptive estimate. So this third type theorem that Bodacic will show tomorrow and Mrs. Club will tell us at what point I should rather believe that the model locally has to be changed or adapted in a way that we will define here soon. So important here is local parametric modeling. Yeah? And let me finish tonight by showing how this local parametric modeling is actually well known since about 42 years. The first local parametric models have been invented, namely by guys like Nadaraya and Watson. Thank you. Let's take a simple example. And suppose I want to approximate this by a constant or by a local linear function. Right? Definitely this is a parabola. I shouldn't try to approximate this by a local linear function. But in fact, if this window here is small enough, it actually looks pretty much locally like a constant. This actually pretty much looks locally like, because of Taylor's expansion, looks like a linear model. So for each x, I can try to model the complex. Complex means I'm out here. Right? I'm trying to model it with something lower dimensional, in this case, parametric linear function. Here it is shown for x equal to 0 and x equal to minus 5. Okay, so the big step now, notationally and in terms of the going to theorem type 2, is that we localize everything that we have seen in the first 2 hours. So we introduce weights W. They depend on X, as I've told you here, weights. Yeah? So maybe locally this looks actually linear, this model. Looks linear. So we introduce weights, and I've told you about 2 hours ago, God probably knows a good weight how to do it because he knows the true function. This is the oracle estimate, and we have to infer from data the real weight. So the local polynomial, local parametric approach consists of now calculating the parametric value in the parametric model with weights. So you see the difference is, this is just a maximum likelihood estimate. Now it's a local maximum likelihood estimate. Yeah, just localized. This is the parametric model, regression model. Don't use any weights, you will get the red function. Yeah? Use weights around a certain point x. You will get for each point x a local model. The question is how to choose this local model. And this is exactly the question of adaptive estimation. For reasons of simplicity, numerical and technical, we use mostly so-called kernel weights. That means we localize by a so-called kernel. And I will show a few minutes I will spend on the form of kernels. And then I think I will stop in about 23 transparencies. So kernels are very well known. Uniform, triangular, financially coordinate, they are all very well known. I don't want to spend too much time on that. The weights can look locally like a uniform, like a parabola, like a triangular, and in non-parametric regression and single-parametric regression, I think Enzo just teaches that. Have you arrived at this result already, Enzo? How to choose the kernel? Very good. This is the Maron-Nolan theorem, right? I don't want to go into that. Volodya told me this is all that you all know that. He actually meant you should all know that, right?
You need not.
You need not. But the bottom line here is, the bottom line of choosing the kernel is this table that says, actually it does not really matter which localizing shape you use. The more important thing is the size of the neighborhood by which you localize. That's in this table. So is anybody here that has not yet seen SPM, the SPM1 course? You? Okay. So I give you a private lesson on this, okay? Also you have not seen it.
That's right.
Yes. Alright. I also give you a private lesson. So, who tells me there's a break because he has to switch the cameras? Okay. So please ask me questions up to now, or ask Volodya and me questions.